Thank you. Yeah, so thanks for having me. I would also like to thank all the people who make this workshop possible. So since this is the lunch talk, I'm trying to be quick so we can have lunch afterwards. So let's see what we can do. So here I will just give you an overview picture. I will work on H, which is a bialgebra. And on this, we are going to have a look at quasi-triangular structures, which will be some elements R in H tensor H. We are going to see what their properties are. Those are also called R matrices, R matrix. And it's well known that those correspond to a braiding on the monoidal category of left H modules. So here we have the tensor product, and the R will give us some braiding. And what we are going to do in this talk is we will add something to this picture. So plus we'll have something that we call an infinitesimal R matrix. And this would be some element chi in H tensor H, which on this side will correspond to some natural transformation T. Maybe I should write T chi here, from the tensor product into the tensor product. And this guy we will call an infinitesimal braiding. Okay, this is the picture. So let's look at this in more detail. Yes, and I should mention that what I'm going to tell you is joint work with 3 of my friends here. Yes. Very good. So here, just one quick slide of what a braiding is. I guess most people know. So just take a C, which is your monoidal category. So you have some tensor product here, and you have a natural ISO sigma that tells you how to flip your objects. And the way how to view the axioms can be written in a nice way here. So you have to look at those first 2 diagrams here. And what this tells you is that if you want to braid an object M with the tensor product of 2 objects, the way how you do this is you first braid M and N, and then you braid M and O. And there's a similar rule if the tensor product is on the left side. Yeah? So here you're just reading this from top to down. And yeah, those are the axioms of a braided monoidal category. From this, you can prove that sigma satisfies the quantum Yang-Baxter, which is written here. So this just means braiding the first, the last. The first is the same as braiding last, first, last. Yeah, very good. So as written in this on the blackboard here, now we are going to look at a special class of braided monoidal categories, namely those that come from bialgebras. So if I have a bialgebra H with coproduct delta and co-unit epsilon, then we look at all the left modules. Yeah? And here the category I will write as HM. And this has a tensor product where I just take the tensor product of vector spaces, but I act on the tensor product using the coproduct. Yeah? And since the coproduct is an algebra map, this gives me a left action. And in a similar way, I can act on the monoidal unit, which is K, so your ground field, using epsilon. Good. And then this is a well-known theorem by Grinfeld and Schan, I would say, proven in 1990, saying that this monoidal category is braided if and only if H is a quasi-triangular bialgebra, meaning that I find this element R in H tensor H, as is written here, which satisfies 3 properties, 1, 2, 3, and it should be an invertible element. And okay, we are going to have a look at those properties in a second, but if I have this element R, then my braiding is of this form here. This is just the action of R and then using the tensor flip. And yeah, this is your braiding. This is a morphism, so it's left H linear exactly because of this property here. So this is a kind of quasi-co-commutativity. And those 2 axioms here just tell you that these 2 diagrams are working, satisfied. Okay, just one comment. So that there's some subclass that is interesting. So in case we have a symmetric braiding, meaning that sigma squares to the identity. So this happens if and only if R is a triangular structure, which just means that the inverse of R is simply the flip of R. Now, but we are working in the general case, so yeah, we don't need this, but this is a subclass that is also interesting. Just very quickly, some examples, so that, yeah, that we realize that most of us have seen this kind of structure. So let's say you have a bialgebra where the coproduct equals the opposite coproduct. In this case, you can take R simply as 1 tensor 1, and your braiding is the flip. So this happens for the group algebra of any group, or for the universal enveloping algebra of any Lie algebra G. So now on the cyclic group Zn, you can even find a non-trivial R in this way here. So you take this combination, which in special case, when you put n equal 2, gives you the super geometry braiding. So there the sigma, this braiding really gives you the minus sign that you see in super geometry. And okay, just lastly mentioning that we have the Grünfeld double. So for any finite dimensional Hopf algebra, we can look at H star tensor H. And on this one, we always find a quasi-triangular structure, just written like this, where EI, lower and upper, is a dual basis. Okay, so this is the known part. Now comes the new part. I hope you can read, yeah. Good, so here the first part is motivating a little bit, and then we give the definition of the chi that I was writing here. So motivating part is the following. Take a bialgebra H. Now look at the topological bialgebra H tilde on formal power series of H that you get by simply H bar linearly extending delta and epsilon and multiplication and unit. And let's say on this topological bialgebra, you are having a quasi-triangular structure, R tilde. And let's read what kind of information this gives us. So first read this in 0 order. In 0 order, we just get some element R, and it's quite easy to prove this is exactly a quasi-triangular structure for H. Very good. So this is an invertible element, meaning we can factorize R tilde in this way. And let's see what we're having in first order. So what is this chi? What are the properties of this chi? And this gives us our definition. So this is what we call an infinitesimal R matrix. And the triple H, R, and chi, we call a pre-Cartier bialgebra. So the definition boils down to this. You start with a quasi-triangular bialgebra, and you take an element chi in H tensor H, which has this commutativity with delta and like 2 extra properties that just say if I apply the coproduct to one of the legs of chi, I get 2 terms. And this you can think of some kind of R twisted primitivity of the tensor legs. Yeah, we will look at this later, and understand how to realize this as some primitivity. Okay, and in some cases, it might happen that R chi will be the same as chi opposite R. And if this happens, we call this triple here a Cartier bialgebra. So yeah, subclass of those triples. Very good. So it's not difficult to prove this proposition. It basically works by definition, yeah, saying that you have a pre-Cartier bialgebra if and only if on your left edge modules you find a natural transformation T satisfying those two axioms here. And this goes back to the picture I was writing on the blackboard. So this is the right-hand side we are getting here. And okay, if you want this extra property of chi, this will give you an extra property of sigma and T. And okay, here on this side, it's really just the commutativity of the braiding with the infinitesimal braiding. But yeah, we don't always ask this. It's only true in some cases. Okay, and some categories that satisfy all of those properties, they will be called pre-Cartier category. Okay, some comments on the definition. Part of this has been known. So in case you take a symmetric braiding, yeah, so when sigma squares to the identity, and you want this extra commutativity with T, you get back the notion of a Cartier category that was introduced in this paper. You can also find it in Kassel book. There's a section about this. And yeah, more recently in a paper of Heckenberger and Vendramin. Okay, but yeah, just saying our definition is more general since we are working with any braiding and we don't in general ask this commutativity of sigma and T. Okay, one more comment. The infinitesimal R matrices chi form a vector space, which also means that 0 always is a valid choice. So here you can see if you take chi equal 0, all of this is satisfied, but that's of course the most boring choice. Yeah. Okay, and secondly here, in the case when we have commutativity of H, you can show that the axioms of chi boil down to chi being an element of a primitive tensor primitive. Yeah, so let's have a quick look. Why is this true? So with commutativity, the first axiom holds automatically, nothing to be proven, and we can move this R -1 to the right side, so they cancel, and we are left with the coproduct here on the second tensor leg is just chi1,2 plus chi1,3, which means that the second tensor leg is primitive. Similar argument for the first one. Okay, very good. So one class of examples I should mention. So if you have a quasi-triangular Lie bialgebra, I'm not going to give the full definition, but it's a Lie algebra where you also have a co-bracket that comes from some element R in G tensor G. For those classes of examples, we can build a chi simply as the sum of R with R op. And this will satisfy all of our properties of our definition. So this would be an infinitesimal R matrix for the Hopf algebra UG with R matrix 1 tensor 1. Another one, maybe I'll be quick on this, is for Sweedler's Hopf algebra. We have not seen in this conference, I think, but it's very simple. You just have two generators, G and X, that satisfy some properties. G is group-like, X is twisted primitive. And on this Hopf algebra, you can find an R. Actually, you can classify all of them. Here I just wrote one. And we classify all possible infinitesimal R matrices on Sweedler's Hopf algebra. And all of them are of this form here. And notice that the only one that satisfies this extra commutation property with R is the 0, 1. Yeah, so this is really one of the more general classes. Very good. Just a quick proposition. We've seen, for example, in talk of Fabio, that you can use a Dünfeld twist to twist your Hopf algebra. And we showed that this twisting process via Dünfeld twist works very well also in this setting. In a sense, you can twist R, this was known, but you can also twist chi in this way. And if you start with a pre-Cartier bialgebra, you're ending up with one of them. Yeah. Okay, maybe the first non-trivial theorem in this setting is the following. So take a triple HR chi, then you can show that chi is automatically a Hochschild to cocycle, which just means that this here is satisfied. And furthermore, you show that what we call the infinitesimal quantum Yang-Baxter equation holds, which is written here. And so it looks a little bit complicated, but it's actually not. So it's, yeah, you see in each of those terms, there are 3 times an R and just 1 time a chi, and the chi is like shifted through, so it appears everywhere to the right of some R. Yeah. Very well. So let me say that part of this has appeared in one of Sean's papers. Yeah. In the example, starting from a quasi-triangular Lie bialgebra, G bracket R. So for those examples here, where the chi is just the sum or the symmetrization of your small r. Yeah. But yeah, here this theorem is for the general setting. Okay, one more comment. If you have not only a bialgebra, but even a Hopf algebra, so if there's an antipode, you can build a Casimir element, or what we call what the Casimir element is. This is, you take chi, it's in the tensor product, so you can write it as chi I tensor chi I, finite sum. And our gamma is S of chi, and you multiply with the second tensor leg. The first nice thing that turns out is that this is a central element. So it's automatically central. This is a way how you can get some central elements. I don't know if this could be useful, maybe. And furthermore, we show that, so if you have a Cartier triangular Hopf algebra, so now we have the commutativity of chi and R, and also that the inverse of R is R op, very special case. In this case, your chi is not only a Hochschild to cocycle, but it's even a Hochschild to coboundary. So those are kind of the trivial, or not trivial, but yeah, easier cases, yeah. And so we can write down that chi is really in the image of the Hochschild differential, and the element that is mapped to chi is the Casimir. So we are taking this gamma here, scaled by a factor, and this will give you chi in this very special case. Okay, just a quick comment. We can do everything in the dual picture. So if you're not talking about modules, if you rather like comodules, we can do the same thing. So there we don't have an R matrix, but an R form. So now R is a linear map from H, tensor H to K that satisfies the dual properties of our universal R matrix. Just very briefly, I show you that the braiding in this case is given by this formula here. So you are using the coaction on the comodule M and N. Here this M0 and M1 is just the coaction. So this is the part in M, this is the part in H. And then you apply R, and this gives you a braiding on the category of right H comodules now. In this setting, you can make the definition of what is an infinitesimal R form. And okay, I think I don't bother you with this. It's just written here. It's exactly the dual definition. So here you don't write the coproduct, but you write the product. And you are not using the multiplication, but the convolution product. It's really the dual statement. And all of the theorems that I mentioned that are working for modules also work for the comodules. So some a little bit more complicated example, some bialgebra that we have seen several times during this conference is MQ2. So take a Q, should be non-zero, and take the free algebra generated by some alpha, beta, gamma, delta modulo the Manin relations, which are written here. So this is, you quotient this out. And you can show this is even a bialgebra using the this matrix co-product here, and the epsilon, which is generators defined like that. Furthermore, you can show that you have a co-quasi-triangular structure. So co here really meaning this is the linear map from tensor H to K that gives you the braiding for the comodules. And the formula on generators is written here. What we showed is that on MQ2, you can find a non-trivial infinitesimal R form, chi, if you take what we call partial D tensor, partial Q tensor partial Q. Yeah. And this will even give you a Cartier structure in the sense that you have commutativity with R. So I just have to tell you what this partial Q is. Partial Q is a linear map from MQ2 into C defined on an element psi just by a rescaling of the co-unit. Yeah. And you can show that this satisfies the Leibniz rule and it's central in a certain sense. Okay. Some more examples. We have GLQ2 and SLQ2. Probably I don't bother you with the definition. You probably know how this works. So just for GLQ2, you have this extra generator that we call theta, which will play the role of the inverse of the quantum determinant. And for SLQ2, you simply set this theta to be 1. Okay, and you can show those are coquasitriangular Hopf algebras with the structure coming from MQ2. Okay, so now we can extend our partial Q to GLQ2 by saying it's okay, it's the same on MQ2, but on this extra generator theta, it should be -2. And you show that also this, so this new chi also gives you an infinitesimal R form. The drawback is that this does not work well with SLQ2. So you can show that this chi does not descend to SLQ2. I mean, it's an easy computation that shows that this cannot work. And it's even worse, we could show that there is no non-trivial infinitesimal R form. So this should not be braiding, should be R form on SLQ2. So that's a bit of a drawback. We hope that maybe on the higher SLQN we can find something non-trivial, but okay. Otherwise, SLQ2 is simply cursed, and yeah, let's see. Yeah, so in the last like 7 minutes, yeah, let's have a look at FRT. So there's this wonderful theorem that tells you how to get examples of co-quasi-triangular bialgebras from solutions of the braid equation. And we are going to give an infinitesimal version of this theorem. So let's first have a look at the standard, well-known theorem. So this goes like this. You are starting with a braided vector space, which is just a finite dimensional vector space with an invertible solution C of the braid equation that is written here. So C is just an endomorphism of V tensor V. You can choose a basis, let's say V1 to Vn, and you take a set of generators of some algebra that you call Tij with I and j running from 1 to capital N. Then you take the free algebra with these capital T's, and it turns out this is a bialgebra using this matrix coproduct and epsilon simply the Kronecker delta. Furthermore, you take a look at the coefficients of C and you call them Cij, Kl, just some numbers, yeah. And you quotient your free algebra by the two-sided ideal IC generated by those capital C's, which are built out of 2 capital T's and having the C ones on the left and ones on the right side. And you can show that the quotient that we call AC from the free algebra, this is still a bialgebra. And it's even better, it turns out this is a coquasitriangular one, where your R is given on generators simply by the coefficients of C with some index flips. So here we have some Ji, yeah. Okay, very nice. This is how we can build a lot of coquasitriangular bialgebras. Let's try to have an infinitesimal version of this. For this, we of course need a notion what is an infinitesimally braided vector space. And definition you can find here. You start with a finite dimensional braided vector space, VC, and then you add an endomorphism T, which satisfies these 1 and 2. And those might look a little bit scary, yeah, like what is all of this? But it's actually not that complicated. For example, if you take C as the flip, you can see that the first one is trivial, nothing to be proven. And 2 are exactly what is called the infinitesimal pure braid relations that were studied by Kono. So we are getting back something that is known in the literature. Furthermore, you can show that for any braided vector space, 1 and 2 are automatically solved if you take as T a multiple of the identity. So this has always non-trivial ways how to solve this. Okay, one less trivial way how to solve it, if we look at a braided vector space that is of diagonal type, which means that C simply flips the spaces and multiplies with some non-zero number, then you can show that if you take T, that is simply the multiplying your base vectors. And here you can go wild, you can set some of them 0, some not, anything, and everything works. Yeah, so all of those will solve 1 and 2. And okay, so here I just gave an easy formula. We even classified all possible T's you can have for this braiding, for this braided vector spaces of a diagonal type. Okay, in the last 2.5 minutes, let's see, I give you this theorem. So we need an extra quotient. So what we are doing is we take now an infinitesimally braided vector space, VCT, and we call T, Ij, Kl the coefficients of T. Those will generate an ideal in AC in this way. And we simply take the double quotients, we further quotient by those guys here. And it turns out everything works. First of all, you still get a coquasitriangular bialgebra, but even more, you are getting an infinitesimal R form, chi, on this double quotient, where the chi on generators is just a T, Ij, Kl. Oh, yeah, and it's basically how this definition was built. So this 1 and 2 are built exactly to make this theorem work. Yeah, since we have seen that we can always find some non-trivial solutions like those here, simply scaling the identity, we can always find on any, for every braided vector space, we can find some non-trivial chi's in this way here. And that's just a rescaling basically of the co-unit. And you can see that the one we have seen on MQ2 exactly came from out of this form here. Just a quick comment. We also have a converse statement saying that if you start with a pre-Cartier coquasitriangular bialgebra and a left edge comodule, you can structure this left edge comodule as an infinitesimally braided vector space by simply taking so chi basically coming from R and T given by chi in this way here. So this is the converse. So now, since I don't have time, maybe I skip Tannaka-Krein, just saying that, okay, in some nice cases, we can understand any pre-Cartier braided monoidal category as coming, as factoring through right-edge comodules of a pre-Cartier coquasitriangular bialgebra. But this, okay, I skip. And just as the last thing I want to say, so this definition gives us a natural deformation problem. So we have seen that if you start with the trivial topological bialgebra and you look at the first order of some r tilde, you will get chi. But now we can ask the converse question. So if we start with h, r, and chi, can we always find an r tilde which quantizes chi, meaning that this r tilde should have chi as its first order? Is this possible? We don't know. It could be a very hard question. We can just, so for some toy models, for some very easy cases, like for Sweedler's Hopf algebra, you can take simply the exponential of your chi, and you see, okay, here it's very trivial since this the second order even vanishes. You can show that this gives you a quasi-triangular structure on h tilde that has chi in first order. But apart from this, we don't really know how to quantize or how to solve this deformation question. And there's the feeling that this should be connected to some Etinghoff-Kashtan quantization problem, but we don't fully understand this. So in case you want to help, you are very welcome. So with this, thank you for your attention. Yes, I said it very briefly. So yes, it was impossible to get. It's so that's a really good question. So like the first motivation was just a natural question to look at first order deformations of braidings. Yeah. But this is not answer your question, which was how can I use this? And so how I think about this, those chi's are kind of like bivector fields. So my aim will be to understand this as some kind of Poisson bivector that might give us some information. Yeah.